Hello, welcome to the video lecture on underwater navigation system. This is part 3 video lecture on unit 1 basics of underwater communication. I am Dr. R. Sandil Kumar, Assistant Professor, Electronics and Communication Engineering, Government College of Engineering, Erode. In this lecture, we are going to discuss about attenuation, absorption, reverberation, refraction, and scattering. First, we are going to discuss about what is attenuation. The main cause of sound attenuation in freshwater at high frequency in seawater, particularly above 100 kHz, is viscosity. Important additional contributions at lower frequency in seawater are associated with ionic relaxation of boric acid up to 10 kHz, magnesium sulfate 10 kHz to 100 kHz. The conductivity of seawater is higher than the conductivity of fresh water. For example, the attenuation experienced by an EM signal at 2.4 GHz frequency for propagation through seawater is above 700 dB per meter, while it is slightly above 1 dB per meter for freshwater. One dB per meter. What is the absorption of sound in seawater? The absorption of sound in seawater is the frequency dependent reduction in sound intensity due to the energy loss. Energy loss in the sense acoustic energy into heat, through viscous and structural relaxation effects and through molecular relaxation process associated with electrolytes in solution in the seawater. Figure 1.3 shows absorption of sound in sea and freshwater. The dark bubble shows the attenuation in dB per kilometer in seawater. The empty bubble shows the attenuation in dB per kilometer in freshwater. The dark lines and dash lines are predicted values for seawater and freshwater. Figure 1.414 shows the absorption of sound by boric acid and magnesium sulfate. Within 10 kHz, the dark bubbles, the attenuation is due to boric acid. Above 10 kHz to 1000 kHz, the attenuation is due to magnesium sulfate. The magnitude of absorption of coefficient in seawater is a function of three components: pure water, boric acid, and the salts of magnesium. For frequencies greater than 10 and kHz and 100 kHz, most of the absorption is due to magnesium salts. Below 10 kHz, boric acid term is important. Above 1000 kHz, absorption by pure water is significant. Scattering of sound waves in seawater. A related acoustical phenomenon is scattering. Scattering is the specular reflection of a wave from small segments of a rough surface. The amount of scattering depends on the size of the object and wavelength of the sound. So, two important factors determines the amount of scattering. One is the size of the obstacles and the other one is the wavelength of the sound. The wavelength of the sound is calculated by using this formula: speed of sound divided by the frequency of sound. The equation for the seawater absorption coefficient at a frequency in kilohertz can be written as the sum of the chemical relaxation process and absorption from pure water. The first term in the total absorption is due to boric acid contribution, and the second term in the absorption is due to magnesium sulfate contribution, and third term is due to pure water contribution. The pressure dependencies are given by P1, P2, P3, and the relaxation frequencies are F1 and F2. Magnesium in seawater absorption. Mechanism in seawater absorption: viscous absorption generated by particle motion. For frequencies above 100 kHz, particle motions generated by the sound produce heat via viscous drag. The absorption converts a proportion of the vibrational energy into heat as it travels through successive specified distance. The coefficient alpha, absorption coefficient alpha, is found to increase with the square of the frequency at frequencies greater than 1 MHz, and it also depends on the temperature, sea temperature in Celsius, and pressure or depth D. Pressure or depth D and sea temperature T, and it also depends on the square of the frequency, right? This term. The second one, absorption by specific chemicals. Two principal chemical components in the ocean which contribute such relaxation frequencies are boric acid and magnesium sulfate. F1 is due to boric acid and F2 is due to magnesium sulfate. F1 and F2 depend on temperature T, but only F1, the boric acid frequency, depends significantly on the salinity S. Salinity is measured by the electrical conductivity associated with the ionic content of the salts. The expression for F1 is set around the typical seawater value of 35 parts per thousand ppt. The other parameter used to represent the nature of the seawater is the acidity or pH value. A typical ocean value adopted is pH is equal to 8. Since pH is greater than 7, the seawater is slightly alkaline solution. The absorption due to relaxation mechanism has a characteristic form: alpha is equal to AX P Fx F square, Fs square plus F square. The X value varies from 1 and 2. If it is 1, 0.106 F1 F square, F1 square plus F square e per pH minus 8 divided by 0.56. This one is due to boric acid. The second term belongs to the magnesium sulfate, where Fx is equal to F2. These values are corresponding to the A2 value, constant A2 value, and the third term belongs to fresh water. That is this term: viscous absorption generated by particle motion above 100 kHz. Figure 1.15 shows the absorption in seawater versus frequency in kHz. The absorption by pure water is given by this blue color line. Is almost looks like a ramp. It drastically increases from 0.1 to 1000 kilohertz, and the green color is due to magnesium sulfate above 100 kilohertz. It's saturated, right, like this. And the red color is the due to boric acid. Boric acid is saturated above 10 kilohertz, almost remains constant from 10 kilohertz to 1000 kilohertz. Transmission loss. Absorption loss and geometric spreading loss on the acoustic wave propagation will give the transmission loss value according to the equation, this one, where the R factor distance is entered because the alpha is usually expressed in dB per kilometer. This one is alpha. This one 20 log base 10. Transmission loss derivation. The transmission loss is given by 10 log base 10 Is divided by I as a function of R. Two major contributions to transmission loss, as already discussed. One is due to the major contribution is due to geometrical spreading. The second contribution is due to the absorption of sound as it propagates. That is given by this value I of R, and this one is IES. Okay. There are several absorption mechanisms. The geometrical loss for ranges less than the transition range is given by TL geometric loss is equal to 20 log base 10 R. For ranges greater than the transmission depth, the geometric loss is given by this value 10 log base 10 R plus 10 log base 10 R transition. Viscous absorption describes the loss of intensity due to molecular motion being converted to heat. Viscous absorption applies primarily to higher frequencies. The attenuation or absorption due to viscous loss is given by this equation. Alpha viscous loss is equal to 4.9 10 power minus 4 f square e power minus t divided by 27 plus d divided by 17 dB per kilometer. The second mechanism for absorption is the relaxation process of boric acid. The corresponding attenuation or absorption loss is given by this equation. And the third mechanism is the relaxation process of magnesium sulfate. Here the absorption coefficient is given by this value. The relaxation frequency F1 corresponding to the boric acid is given by this value. The relaxation frequency for corresponding to the magnesium sulfate is given by this value. The total transmission loss is given by this one, geometric loss and absorption loss. Absorption loss contributed by three values: viscous loss and loss due to boric acid, loss due to magnesium sulfate, and R is the range or distance. The range is usually in underwater communication is in the kilometer range. For phased array system, all absorption model parameters are fixed at T is equal to 10 degrees Celsius and 35 parts per thousand, and pKh is equal to 8. Refraction and Snell's law. When an ultrasonic or EM wave passes through an interface between two materials at an oblique angle, the materials have different indices of refraction. Both reflected and refracted waves are produced. Refraction. What do you mean by refraction? The change in direction of acoustic wave as the ultrasonic beam passes from one medium into another having a different sound velocity. A change in both direction and mode occurs at acute angle of incidence. At small angle of incidence, the original mode and a converted mode may exist in the second medium. So what is refraction? The change in the direction of acoustic wave as the ultrasonic beam passes from one medium into another medium due to different sound velocity, different refractive index. The Snell's law describes the relation between the angles and the velocity of the wave. Snell's law equates the ratio of material velocities v1 and v2 to the ratio of the sine of incident and refracted angles as shown in the following medium. VL1 is the incident ray, VL1 dash is the reflected ray, and VL2 is the refracted ray. Both VL1 and VL1 dash both are traveling in the medium 1, and VL2 traveling in the medium number 2. Theta 1 and theta 2 are incident and reflected angle. Theta 2 is the refracted angle. When a wave moves from a slower to faster material, there is an instant angle that makes the angle of refraction for the wave 90 degree. This is known as the critical angle. Reverberation is the persistence of sound after it has been stopped due to multiple reflections from surfaces such as furniture, people, air, etc. These reflections build up with each reflection and decay gradually as they are absorbed by the surfaces of objects in the enclosed space. Reverberation definition: this prolongation of sound in a hall even though the source of sound is cut off is called reverberation. Reverberation is dependent only on the volume of space and acoustically absorbed the quality of the room's finishes. Here two examples are shown for reverberation. One is in the open stadium, another one is the closed stadium, right? Reverberation is dependent only on the volume of a space and the acoustically absorbed quality of the room's finishes, that is the room material. Hello.